confirm receipt of command, over. Flight payload, curtain start, over.
Copy that, payload.
We should be looking for some signs of the impact on the leftmost part of the...
Standing by with mid-infrared changes.
The left side of the shadow, right below the dimpled crater on the crater, the larger crater rim.
Flight, this is Science. Make the rate changes. MIR 1, 1 hertz. MIR 2, 0.1 hertz. Over.
Copy, Science. Command flight. MIR 1 to 1 hertz.
Sending MIR 1 at 1 hertz.
And the science team is directing the flight team to adjust the sampling rate of some of the instruments to fit within the 1 megahertz.
Ready with MIR 2 at 0.2, at 0.1.
The 1 megahertz signal limit.
Go flight.
Command flight. Send MIR 2, 0.1 hertz.
MIR 2, 0.1 hertz. Sending command. Flight confirm receipt of command, over.
Copy that, payload. All stations flight 1 minute to transition to DV mode.
Transition to DV mode, which is Delta V mode, actually is a control mode for the spacecraft. It allows us to slew much more quickly, to continue pointing at this suspected Centaur impact point, even though the shepherding spacecraft will be impacting a couple of kilometers away. This is the last minute before the shepherding spacecraft also impacts the surface of the moon, and the last minutes of flight. We're watching the remaining few seconds of the LCROSS mission as we approach very rapidly the surface of the Cabeus crater.
Mark, transition to DV mode.
Flight.
Payload confirm crater mode
NIR 2, OPR change request. NIR 2 to OPR 10. Over.
That November. NIR 2 to OPR
Yes, confirm.
10.
November.
Ready. Command flight send November IR 2 to OPR 10.
Command sent. Flight payload confirm receipt of command.
Copy, payload. Stand by for shipping spacecraft impact.
The very last seconds of the shepherding spacecraft trajectory as it approaches the lunar surface. We are seeing very small craters within the crater.
We confirm a thermal signature of the crater. Our mid-IR cameras. Over.
Copy, science.
We just received
flight shepherding spacecraft impact. Stations report LOS.
The ground stations at Goldstone just reported
last packet 11:35:35.054 seconds.
The shepherding spacecraft has hit the surface of the moon, and this marks the end of the LCROSS flight mission. Hit the surface of the moon, and this marks the end of the LCROSS flight mission.
Okay, all stations flight. Great job. First step 179, complete closeout of your flight products and get them on MDPS.
Well, Michael, I wonder if you could give us your impressions of what we just saw and mission success.
Well, it's hard to tell what we saw there. I'm not sure. I'm not sure if the gain was set there correctly or what. We had some confirmation from the mock that they did have a thermal signature.
Yeah.
I should mention that the 9 instruments on the trailing spacecraft, the LCROSS spacecraft, were exercised on the way to the moon. In fact, we took images on the way and images of the Earth, so we're confident the instruments performed as expected. At the time of the impacts, the mothership, the Lunar Reconnaissance Orbiter, our sister ship, I should say, was about 50 kilometers overhead. They will have their first, and so they should have been seeing this with their suite of instruments. They do their first data downlink in about 2 hours or so. So we hope to have the data, and I expect we will be receiving both imaging data and spectroscopic data from the host of ground-based observatories probably within the next few hours. I think it is fair to say that within this $79 million cost cap, as I mentioned earlier, the experiment had been optimized to produce the largest possible impact plume, and so I remain confident that this is our best opportunity to date to measure the extent of water ice on the moon.
So what we're seeing here is a replay of that impact. Let's watch it for a little bit.
Now, even though there were 9 instruments on the trailing LCROSS spacecraft, which you see going in here, they basically break into 3 categories. There was something called a flash radiometer, which should have seen the flash, and by virtue of analyzing that signal, we can make some inferences about the depth of the regolith and it's the makeup of the dirt, as it were, that was thrown up by the Centaur impact.
Right. So brighter flash means, you know, it hit rock, and dimmer means it hit dirt.
Right, and actually you would want a dim flash here because that is suggestive that you hit sandy material and you want to throw up as much of that as possible, and that's easier to throw up than boulders. Then there's a suite of cameras, visible, near-infrared, mid-infrared, that provide information once we analyze the signal, once we analyze the data on the shape of the ejecta cloud, which contains both regolith and hopefully water vapor. It tells us about the dust grain properties in the ejecta cloud and provides spatial context for the spectrometers. And then finally there is the suite of spectrometers. And most of the information, much of the valuable information, will come out of the near-infrared spectrometer, which provides analysis of the chemical composition of the vapor in the regolith and any possible hydrated minerals.
Michael, we've just brought up the
thermal infrared.
Yeah. I wonder if you could comment a little bit on.
Well, the blue areas are the cooler regions, and so the green and the red are increasingly warm regions, and so you can imagine the sun beating down on the south rim of that crater. That's why it's showing up as red. This is all false color, of course. And of course we're aiming for the blue region, which is the permanently shadowed region here. The reason you have this many instruments is we're trying to tease out, particularly with spectrometers, the way I like to phrase it to people is we break light into its color constituents, and then we look for little squiggles superimposed on big squiggles.
Yes.
And the little squiggles are hopefully the signatures of water and other hydrated minerals. The big squiggles are just the electronic noise in the cameras, and so even though the data will become available to us in the next few hours from the other orbiting and ground-based assets, I anticipate it will take a couple of days before we can calibrate out the big squiggles and get into the little squiggles. And we want to have some redundancy in the instrumentation. That's why we have multiple instruments looking at slightly different wavelengths. So the whole idea here is to collect as much data as you can and minimize any ambiguity in the interpretations as you try to analyze those small squiggles.
Well, we have redundancy not only on LCROSS, but of course with all the ground assets from the Earth, the Hubble, and LRO, like you mentioned.
As we begin to collect the data and we analyze it, If we don't find water, is that a significant finding in itself?
It is, because of the reasons I stated earlier, excuse me, it has been